So anyway, I want to talk about what are the general patterns that people see in trying to build big data applications. And I'm going to leave some time at the end so we can talk about your big data applications, how those can be built, how those can be shaped. My name's Ted Dunning. I work at MapR. That's why I wear the red hat. Actually, I wear the red hat just so I look like a trucker when I go to the Midwest. But I claim to fame is I've been involved in open source a long time, bought the drinks at the first hug, and currently work on a lot of open source projects as well as helping MapR customers. MapR distributes open source components with a heavy technological wrapper that allows much higher performance and a whole lot of enterprise sorts of capabilities using standard APIs. Standard APIs like POSIX, like NFS, like HDFS, and MapReduce. You can get a hold of me all kinds of different ways. I'm sure you can find my email on the web. I don't care if it's out there. Just holler if you want to talk. So what I want to talk about first are some of the universal driving factors. One thing that people kind of miss out on is the fact that nobody clearly explains why big data is happening right now across a huge range of industries. There's a real mystery there of why big data techniques are being adopted in a way very different from every other technological revolution that we've seen. Timescale, rationale, all of these things are different in this time around. It's not the same. I'll talk about that very quickly. And then I'm going to talk a little bit about how you diagnose what the general shape of what you're trying to do is. Reasoning from almost business level down to the kind of application you have. And then I'll give some examples of big storage, aggregator machines, things like that, percolator style, search abuse. Search abuse is my favorite because it sounds so bad, but really it's so good. So the first thing that we want to worry about here, I have to move the mic, is why big data scales and how it scales. And a lot of people pay more attention when I put real money on the table. So let's do that. It's a $20 bill. It's a $5 bill. There, okay? And a $1 bill. For completion, we should probably use something else too. A coin, 50 cents. And most of all, my hat, okay? Now, what am I going to pick up first? We got data just laying around. What am I going to pick up first? 50 cents, $20, what? Well, obviously, it's my hat. It's the most valuable thing I've got, of course. It's trademark, it's identity, things like that. Then I'm probably going to go for $20. Would you do that? Say what? Yeah. Well, but which one would you pick up first? Not whether you're such a person that $20 wouldn't be worth it. Which one first? $20 or $1? 20. Yeah. I'll ask the practical person in the front here. And that's all it takes to make you halfway to being a data scientist. Data scientists pick up the most valuable bytes first. Duh. They try to anyway. He says no. They pick up the least valuable first. Over the last 30 years, in fact, they have tried to attack the most valuable problems as far as they could tell first. And they have left things that have very low value density toward the end of the task. And what this means is that every data mining problem shows a pattern of diminishing returns. And you see something like this graph here. These are arbitrary quantities here, arbitrary size scale here. Bigger is that way, more valuable is upwards. And so because they pick up the more valuable bytes first, analyzing more and more data has less and less value density over time. Okay? So what we're trying to explain here is why banks and startups and big and small companies are all adopting big data techniques at the same time. If it were just a value threshold banks would probably do it first because they have a much higher value per byte of data than, say, startups doing online advertising. And in fact, it's not true. Online advertising came a bit first. If it were just technology openness, startups would have done it long before. But in fact, big companies are doing it as quickly as startups. And so we have this mystery of why is it that people are jumping on big data simultaneously? The first part of the mystery is this diminishing returns. The first bytes are more valuable than the last bytes. And that's purely based on the selfish desire of people to, and on the average, reasonable accuracy at picking up valuable bytes first. Now, cost traditionally has gone up in an accelerating way. That's just an artifact of the way we do business. Now, traditionally, we do things like alter table, and those operations contribute to those accelerating costs. So one thing that contributes is the desire to scale up instead of scale out. Scaling up causes us to go to more and more elaborate and expensive technology. But even subtle things like alter table, any sort of change to existing data requires QA. And the more data we have, the more QA it causes. And so the cost of doing something like changing existing data gets bigger and bigger and bigger, and that causes accelerating costs. Now, the difference between these two, the value and the cost, is the net value. That's what this is here. And it's pretty easy to see that if this gets flatter and this gets steeper, then this point in the optimum is where they have the same slope, and that's going to occur before the cost gets steep and before the value gets flat. Just a natural function of the shape of these, unless we go to very, very extreme scales of these things. But it's always going to look kind of like that. And so we're never going to get an optimum size to the right of that corner. Never going to happen. Just because one gets flat and one gets steep. Okay? But if we change the shape of this cost, if it becomes linear, and especially if it becomes linear and much flatter, then we have a very different situation, and the net value begins to flatten out dramatically. And as the cost curve becomes flat enough so that it's comparable to this curve, the optimum point, where you would imagine a bubble sitting in here, a bubble would race out this curve, 4 orders of magnitude change in the optimum scale. So this is the first shape of data sort of argument here today. And that is that causing costs to become linear causes a profound and sudden change across all sorts of data exercises. All kinds of ways of looking at data change dramatically, and this is why this changing shape is what happens with big data techniques. And that is why people are doing it across all kinds of industries, because all kinds of industries have diminishing returns. All kinds of industries previously had accelerating costs. All were trapped to the left of that corner, and they're all being released at the same time. So that's a key intuition. We have to, as we go forward and look at these examples that I'm presenting today, we have to look at them and say, how is it we're going to get linear costs, linear scaling costs, truly linear? Machine time, machine costs, acquisition of the data costs, and the human costs. All of those have to become linearized to get this revolution. So let's look then, what kinds of architectures actually come up in real situations. We've had a couple just now, and a little bit on the streaming side. Informatica, very, very good at ETL, good partner of ours. SQL Stream, very, very much an emphatic advocate of streaming. But those are just a few kinds of things. So we can do kind of like what they do, what biologists do when they make a taxonomy of species. We can build this is the top end of this taxonomy, a taxonomy of big data. So first question is, how big is your data? If it's not big, you don't have a big data problem. People forget that. This is actually very common. An awful lot of data sets are small. If it ain't broke, don't fix it. Come back later when it gets bigger, or not at all. Now, it's surprising that 90% of the Hive jobs at Facebook, big data, you know, they feel all muscular when you talk about Facebook. 90% of the Hive jobs process less than 10 gigabytes there. So interestingly enough, the advantages over here can drag along an implementation technique over here. People may use big data techniques somewhat inappropriately for the sake of consistency. So the game isn't over when we get to A. But in general, if all of your data is small, if you have an OLTP type problem where the databases are typically small, I think 95% of databases, 99%, somewhere in that range, are less than 10 gigabytes if you look across all of the world. If it's in the mid-range, it could go either way, depending on the characteristics of the processing that you have to do. You may need big data techniques to process things that are 100 gigabytes in size due to special things that you do to them. But often, you'll get to do those in the small data style. If it's large, I mean, around 200 gigabytes, it begins to become emphatically large. Below that, we have an interesting question of what kind of queries do we have? Do I want to be able to just go in and pick an element that I know by name? So for instance, on YouTube, you follow a link and it returns you the video. The link is the name, essentially, of the item. The video is the data. So you're getting it by name. You're getting, that's good to get reminders like that. One wouldn't want to forget. So if you're getting one single element at a time like that, or if you have billions of images on a website, you're trying to get a particular image of a particular document. Things like that really are big storage. You're not really trying to do analytics across these things. You very often have a gazillion of the things. They might individually be quite big. You might have an ingest problem where once you ingest one of them, you may need to make 100 versions of it. But once that happens, they become fairly static. You usually have low bandwidth access patterns, at least per byte. The number of bytes per byte that you're analyzing becomes low, bytes per second. So you get into the big storage thing. Now there's nuances in big storage, but that's kind of the category you go into. If you want to make one pass over 100% of the data, you're probably best off using streaming. Possibly big streaming if your data is very fast. What's fast? Well, Twitter is kind of a boundary that people talk about as being kind of fast at a few thousand per second, maybe 10, 20,000 per second, a few 100 million a day. But we have customers who are handling several million items per second. These are entire new documents that they need to index and process at that sort of scale. So you can have streaming and you can have big streaming or really fast streaming. If you want to make mini passes over big chunks of your data, not just point queries, then you probably need to look at what's your response time. If it's less than 100 seconds or in this kind of human scale, then you need to go down into the ad hoc query area. If you really want throughput, not response, but you're doing a lot of kind of ad hoc queries against that, you need to go down in here, which is the classic Hive sort of things, the throughput-oriented data processing systems. And when you look at any given sort of application or business need, what you wind up with is kind of a subset of this. I mean, you might be starting out with streaming for ingest and then flip over to big storage. And you can draw a nice little diagram of how your application fits into these needs. And any given development team will probably be only working on one piece of this. So let's talk a little bit now. Does it make sense? I mean, most people don't talk about what the real shape, what the underlying reasons and rationales for why we do what we do are. But I think it's really important to start thinking that way so that if you have a business selling livestock and another one analyzing tweets, if there are essential properties, the essence of what they're trying to do with their data may well be the same. One might be looking at ear tags on cows, another might be looking at radio locators on garbage trucks, another one might be looking at what do vending machines say in real time, and another one might be doing streaming tweets. In fact, those have grave qualities that are very, very similar. And we need to see the commonality beyond the superficial differences. This is the same thing that made mathematics successful, is that you can generalize it from place to place. So here, let's talk about these. Big storage, characterized by a primary mission of preserving data at rest. And occasionally, at least relative to the scale of the data, you get a piece. It becomes quieter and quieter the larger scale you work on typically. So if you have a big storage problem at 1 or 2 terabytes, very often the data becomes very hot. As it moves up to petabytes or hundreds of petabytes, the average bandwidth per byte of stored data becomes very, very low. People don't look at most of the data, thank God, most of the time. And that's partly due to the bandwidth of the pipes leaving this thing. But you may still need to require all of that be stored for a very long time. So often we have 100-year storage times requirements here. So imagine user-generated videos, a YouTube-ish kind of business, but at much smaller scale. Imagine only 10 million videos. But one of the first things you do to videos is you generate thumbnails. You generate those thumbnails all through the video, typically 64 places or so, and then you put them into different resolutions. You also may re-encode that video into 5 to 10 different formats. The result is you've got hundreds of files associated with a single video, and so only, in quotes, 10 million videos winds up needing 5 billion data assets that all have to be held in some coherent way. That's big. That's a lot of things. And these are actually pretty big things. And so immediately you wind up with hundreds of terabytes or more of storage. And in the past, building this, I can say from personal experience, is extremely unpleasant. Unless you have new techniques that unify these sorts of things. Here's another one. If somebody is going around photographing public documents, church registers all around the world, and bringing back digital images of that, say for genealogy, one of our customers does that, the largest genealogy site around. Well, every page can't be kept in the original, well, it must be kept in the original resolution, but it can't be presented in the original format and resolution. It's often a TIFF file. It's often very, very large. So we're going to recompress that, and we're going to get different resolutions of it. We're going to put combinations of multiple pages together so you can see a whole single image will display many pages for efficiency on the web. And again, you're going to have many, many copies of the same file for presentation purposes. And immediately you have billions of these items, some of them large, some of them small. Corporate document archive is another classic. Anybody ever bought a house? Remember all those pages in the loan package? Those all have to be digitized in the modern world, and they have to be kept for the entire life of the loan. And every time the loan is transferred, they generate a new packet of documents. Every time you refinance, you get a whole new stack. And so very quickly, over the life of your ownership of the house, you've generated a document stack this high. Those are digitized. They have a 30 to 50 year retention requirement at the bank. They have to be able to pull back any one of those, and they have to do a little bit of processing on them. Change the resolution, recompress, maybe do OCR against them. And so they wind up with billions of files that they have to keep for a long time. But again, there's no longitudinal queries across all of these, typically. Might be once or twice to rescale things or to do the OCR, but big storage is a stable sort of thing. Aggregator machines is another big pattern. That's where you have a lot of data coming in, and in real time or near real time, you need some aggregates, often very, very many aggregates, to be produced. And the classic mission for these kinds of companies is to answer questions like, how many actual households in Seattle were watching whatever TV program? I'm sad to say I can't mention any current television programs. I should be happy to say that, I guess. But how many people were watching the reruns of I Love Lucy, where we produced a used car ad last night at a particular time when the ad ran? So 5-minute windows. Every 5 minutes, they aggregate this for all of the markets across the country, all of the different digital sort of cable things that you might be watching. And they need to be able to very quickly, in a few milliseconds, answer any query like this for their customers. So what they do is they produce associative kinds of aggregates. So if they're going to be asking how many unique, they will put together an approximate unique type data structure, something like a hyperlog log counter or something like that. And these have the property that you can glue them together. So I can take this unique counter and I can take that unique counter, glue them together, and I can find out how many uniques were in those two together, even if there were duplicates across those. They also keep track of things like you can't be in Chicago and Seattle at the same time. And so you can just add the uniques from those cities. You don't have to keep fancy data structures. But they have to keep a lot of those. And they have to do it on a near-flowing sort of thing. This is a very common pattern among ad companies, among statistics companies, things like ComScore, RentTrack, Quantcast. A lot of these people have to do this. It's a very common pattern of big data. Less common, but much more powerful, are percolators. This is used ubiquitously, for instance, at Google. The way this works is you have an incoming ingest. You have to store something reliably and permanently with a very, very short SLA on how quickly you do the storage operation. Now, there's a lot of additional processing you need to do as well. And you need to do that additional processing as soon as possible. But there isn't an absolute real-time constraint on the as soon as possible part, merely on the ingest part. And the reason for this differential is so that when there's a flash load of some kind, when the ingest suddenly goes 100x what it's normally been, we want to devote all resources to ingestion, because that's where the guarantee has to be. We will catch up later on the as soon as possible side of things. And normally we'll be within under a second on the as soon as possible, possibly a few hundred milliseconds. But when the shit hits the fan, it has to be stored stably, and all the rest can wait for a little bit. And so that's what percolating is all about. If we have documents coming in and they have to be indexed, if they have to be summarized, the indexing and the summarization can wait. If we have images coming in and they have to be sprited and moved into different formats and things like that for analysis, that can wait compared to the ingest. There's a very, very common pattern here. And you absolutely have to have that load cut away so that things will continue to function correctly. You see this in both of the previous two patterns. You see this in the big storage cases where just getting it stable and safe is primary, presenting it as secondary. You see it in the large-scale aggregator machines where ingesting the data is the first priority, making sure it's stable and safe. The second priority is to produce those aggregates. If those are late, it's one thing. It's not good. It's not so bad, though, either. Losing data is horrific to these companies. And so percolator design is very, very commonly done. And one of the standard ways to do it is just exactly the way they do it at Google. You stick something into a columnar data store, like HBase, And the properties of columnar data stores is different columns of data can have very different storage properties. We can, in fact, say one column family is pinned into memory. And we know that, and if that column family represents whether something has been processed or whether there's pending work to be done, we know that there's very little pending work to be done because we're mostly up to date. That means that column is very, very sparse. Only a few things will be stored in memory. And we can search through that bunch of nothing very quickly and find the few somethings, find the few flags that actually express that we have something to process. And so when we insert things, we insert with that flag set, I need to process this, and the percolator scans for modified flags, scans very quickly, and processes the records and clears that flag. So we can get that percolation happening very, very soon after the ingest, but it's guaranteed that this process will fall behind if the ingestion needs the resources. Our company by flamenco guitarists. Flamenco guitarists play guitars that play in this style. In this style originated in this geographical place. Paco de Lucia plays guitar. He plays music from this place. And therefore we have a match. It looks like people have engineered that. And people have. This is the promise of big data, is that people will do our work for us. They will tell us about the world. And these techniques can all be put together using what I call enterprise mining. This is where multiple groups within an organization have data mining needs. They're building models. They're building new features that these models live on. They're building systems like we just saw. And some of them are very, very good at what they do. Some of their features really ought to be recognized and reused in other areas. So I've got customers who have 1,400 people building models. You know they don't all talk to each other. They live on 3 continents. So what would be nice is if they could express the things that they're doing, the computations that they're doing, with goes-ins and goes-outs and a quick description. And if we could further elaborate that description with credibility or reputation, and we would be able to also augment it with people who like to build models that are described this way, really like this feature, that social search, that behavioral search. And then also have the system compute these values using percolator style for all of the customers. So if an external factor changes, all of the percolating variables will change. And if somebody changes a version on something, suppose I make an over 35 flag. Turns out it's really valuable. And I realize later that I really coded it up incorrectly. It's really an over 45 flag. So I immediately fix that because it's obviously wrong. That becomes version 2 of my over 35 flag. It's actually correct. But a lot of people depend on version 1. So they'd say, I depend on version 1 of the over 35 flag. When I declare there's version 2 available, their models automatically version, and we can now test those 2 models to find out if they're happier with my corrected version of the flag or happier with the broken version, which happened to have a very felicitous bug in it. By allowing all of this version control, allowing all this percolating, and allowing the reputation to manage this, we can hook these siloed data mining groups together so that they can use the valuable experience of other groups, come up to speed more. So I presented 5 concrete examples of how these systems can be done, the big storage, the percolator, the search abuse, the enterprise mining. I've shown a little bit of the questions you ask at the front end to get down to these things, and shown you at the heart why we see a revolution happening. There's got to be some questions. Anybody have any?
Why do you call it abuse?
Abuse? Because I got in trouble when I was a kid when I misused things. People said, that was intended to be used this way. And I go, well, it's really cool if you twist it and you do this. Like, ever melt crayons? You can do some really cool stuff. You can make paint, things like that. But that's abuse. You're not allowed to do that. Well, I'm still doing it. You're not supposed to use a search engine for non-text. That's what it was intended to do. Well, let's abuse it. Let's melt it. Let's reform it. That's why I call it search abuse. Besides which, it gets people into talks, and they pay attention. Yeah?
One of the places that I run into the MapR stack is on Amazon EMR, and there's a couple flavors of that.
Mm-hmm.
Could you talk really briefly about what those are? And,
Happy to. I'm really glad I still have the hat on so that I don't have any sort of vendor-neutral illusions going on here when I answer a question like that. So MapR is exclusively partnered with Amazon and with Google for their cloud offerings. All of the normal versions of MapR are available in both settings. The MapR comes in versions as time progresses and we get better at stuff, and editions. The editions relate to the license that you have for different advanced capabilities. We have 3 editions right now. M3, free, runs as fast and as big as you want. No limits on scale or performance. It will not do mirrors and snapshots. It will not do full HA. It's fully durable. It's very hard to kill it. So, it's got cool stuff, make it sit as good or better than any other version of Hadoop, but it's free. M5 adds all of the HA and data survival features. Snapshots, mirrors to send to another place, control of topology, where data lives in a cluster, exactly, where jobs are run in a cluster. You can have an unlimited number. It's a fully distributed NFS server. You can put an NFS gateway on every machine that's doing any processing. So you can have terabytes per second of NFS bandwidth to the cluster. And that's really exciting because then just, your home directory can be on there. You can run all kinds of applications on the big data cluster, and then they can coexist with big data applications. M7 adds tables. Tables are an HBase API compatible reimplementation in the file system layer. So it gets rid of all of the extra processes, the extra network hops, increases performance over HBase about 4x, decreases latencies massively, especially if you care about latency, you care about guarantees and maximums. So if you're doing inserts into HBase, you could sometimes hit 20 or 30 second response times. You won't see anything over 600 milliseconds, and the average will be down around 10 milliseconds on M7. Now, this doesn't answer the question of what comes next. It could be odd numbers, it could be prime numbers, we don't know. But those are the 3 editions that we have right now. So, and if you have any questions about that, I'm happy to talk about it till you will be so bored of it. I love talking about this stuff. Any other questions? I'm probably out of time, right? Mens does something. He says, last question. Any last questions? So if you need to get in touch with me, there you go. ted.dunning@gmail, tdunning@Apache, tdunning@MapR Tech, any way you like. And I love to answer questions. I love to help folks. So ping me. Thanks for coming.